Now we discuss Langmuir adsorption isotherm. Irving Langmuir presented his model for the adsorption of species onto simple surfaces. Langmuir was awarded the Nobel Prize in 1932 for his work concerning surface chemistry. Langmuir adsorption model is the most common model used to quantify the amount of adsorbate adsorbed on an adsorbent as a function of partial pressure or concentration. Now we see the assumption of Langmuir adsorption isotherm. These are gaseous molecules behave ideally, only one monolayer forms, all sides on the surface are equivalent, no adsorbate-adsorbate interactions, an adsorbate molecule is immobile. He considered the surface of the solid to be made up of elementary site, each of which could adsorb one gas molecule. Now you can see how the gas molecules are adsorbed on an equivalent sides of the metal surface. It is assumed that every adsorption site is equivalent site. The ability of the gas molecule to get bound there is independent of whether or not the neighboring sites are occupied. In schematic diagram showing the equivalent sites of the metal surface, now we can see how the gas molecules are adsorbed on the equivalent sides of the metal surface. It is represented by red color lobes. Here also you can see the vacant sites, equivalent vacant sites on the metal surface. It is denoted as blue dots. He further assumed that a dynamic equilibrium between the adsorbed molecule and the free molecules. A is a gas molecule and M is the surface site, then A plus M giving forward reaction as AM. This AM giving back to A and M in the backward reaction. So this is an equilibrium reaction. So this is adsorbed site and this is vacant site. K is the rate constant for adsorption, Kd is the rate constant for desorption. The rate of adsorption is directly proportional to the partial pressure of A and the number of vacant sites on the surface, that is n into 1 minus theta. Pa is the partial pressure of A, n is the total number of sites, theta is a fraction of surface sites occupied by the gas molecule. So rate of adsorption is directly proportional to Pa into n into 1 minus theta. Theta can be calculated by number of adsorption sites occupied divided by number of adsorption sites available. The rate of adsorption is equal to Ka into Pa into n into 1 minus theta. Here we removed proportionality by introducing the proportionality constant Ka, that is rate constant for adsorption. Similarly, we calculate rate for desorption, that is Rd, rate of desorption is directly proportional to the number of adsorbed molecules, that is n theta. So Rd is equal to Kd into n theta, where Kd is the proportionality constant, that is rate constant for desorption. Since at equilibrium, rate of adsorption is equal to rate of desorption. Now we compare these two equations. It is Ra and Rd. Ka, Pa, n into 1 minus theta is equal to Kd n theta. By bringing this Kd into left hand side, we have new rate constant capital K, where K is equal to Ka divided by Kd. The equation becomes capital K into Pa into n into 1 minus theta is equal to n theta. We have common n on both sides, so remove this n in this equation. Now we have new equation 1 minus theta divided by theta is equal to 1 by Kpa. By rearranging this equation, we get new equation at last, that will be theta is equal to kPa divided by 1 plus kPa. This is called Langmuir adsorption isotherm. Now we plot a graph between theta versus pressure. The magnitude of adsorption at a given temperature should first increase in proportion to increase of pressure and later on should tend to attain a certain limiting value. At very low pressure, the equation becomes theta is equal to kPa. Since kPa value will be very low value, that will be negligible, so equation becomes theta is equal to kPa divided by 1. So theta is directly proportional to partial pressure of the gas molecule. So the order of the reaction becomes 1. At high pressure, the kPa value is very high, so N becomes negligible compared to kPa. So the equation becomes theta is equal to kPa divided by kPa, theta is equal to 1. So the order of the reaction will be 0. Since according to Langmuir theory, only a single layer of molecule is adsorbed on the surface of the adsorbent, the fraction of theta gives measure of the amount of the gas adsorbed per unit mass of the adsorbent. In the next videos, we discuss the questions in this chapter which is asked in CSIR exam. Thank you.